We are briefly going to review some field laws as well as introducing a new one. And what we're trying to do here is work towards two things. One is ultimately having all of Maxwell's laws. And so in a later video, I'll present what Maxwell's laws are and tell you why you should care. Along the way, we have to modify one of the field laws that we've already met. So first, we're going to go through the ones that we don't have to fix, which does actually include a new one. So first is Gauss's law. Remember, Gauss's law was the thing where you had to enclose a charge in a fake surface and use symmetry to pick which surface it was, and then you integrated the electric field over the surface, but in general, you actually just did a multiplication problem. Yeah, that was Gauss's law. And so that told you the flux through a closed surface, which is just this is like the definition of flux, is equal to the charge enclosed over epsilon naught. And we use symmetry to actually make this problem doable. So this is one of our fundamental equations. This tells us the nature of the universe. This will be one of Maxwell's laws. Cool. So this was for electric charges and electric fields. Well, all charges are electric, but electric fields. We are now going to have a version for magnetism. This is new. It was kind of presented along the way, but we don't make a big deal out of it, because it's not really useful. The magnetic equivalent of Gauss's law says we take our object, our magnetic object. When I say magnetic object, I don't mean magnet, I mean object creating magnetic field. We enclose it in a surface, a Gaussian surface. We do our integral of the flux and we get 0. Why do we get 0? Well, if we think about, say, charge enclosed, where this is now the magnetic equivalent, whatever that is, notice that we always have opposite values here, right? Remember that we always have a north and a south. So if you can never separate your north and your south, you're always enclosing those together, right? We could have two little things, but effectively the equivalent of our charge for magnets are north and south, which are inseparable. You can't just have a north by itself. So what that means is the net flux from magnetic fields is always 0. Why? Well, look, we have out, 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 and then we have in, in, and those are equal. And there's nothing you can do short of having a north pole by itself or a south pole by itself to change that. So this is the magnetic equivalent of Gauss's law, and as you can see, it's just not that useful. So it's like Gauss's law, but it's always 0 because we can never enclose a north or a south by itself. So this is new, and the only reason we're talking about it is because later it will appear as part of Maxwell's equations. Now we have Faraday's law. So Faraday's law was the idea that you can have an induced electric field from a changing magnetic field. Now we typically talked about that originally as induced current, but then we pointed out that you can remove the wire and your EMF or your field is still there. So EMF was just the path integral of our electric field, and so that's basically plopping down a circle and then integrating over the circular path. So this is now relating to our electric fields, and then the way that our magnetic flux, so the sub m here means magnetic flux, is changing with time. So this is familiar, and again, it was something we covered kind of at the end of chapter 30. So these are our two familiar things, one trivial new thing that's still familiar, and from here we're going to move on to modifying one other law.